Now we will learn about the correlation coefficient R, properties of R. So measuring linear association, a scatter plot displays the strength, direction, and form of the relationship between two quantitative variables. Linear relationships are important because a straight line is a simple pattern that is quite common. And our eyes are not always a good judge of how strong a relationship is. Therefore, we use a numerical measure to supplement our scatter plot and help us interpret the strength of the linear relationship. The correlation, which is represented by R, measures the strength of the linear relationship between two quantitative variables. So in this formula, we can understand this R equals to 1 divided by n minus 1, and this is symbol of summation. So it is nothing but add these terms for all the individuals. So if we do not want to use this symbol, then we have to write the whole thing again and again. So here we can see R is equal to 1 divided by n minus 1, xi minus x bar divided by sx to x2, then y2, then x into yn. So this is simply doing the summation. And here we are standardizing these variables. So we can sometimes we can also say that we are using the product of z-scores of both the variables. So here x bar is and y bar are mean respective of x variable and y variable, and sx is a standard deviation of x and sy is standard deviation of y. So here we simply can understand that we are standardizing the variables and taking the summation of the variables product and taking its average. So I will explain it in few words. So it is an average of the products of the standardized x and y for the n observation. Here we are using n minus 1. So we say a linear relationship is strong if the points lie close to a straight line and weak if they are widely scattered about a line. The following facts about R help us further interpret the strength of the linear relationship. Properties of correlation. Correlation is represented by R, and R is always a number that is between -1 and 1. R when greater than 0 indicates a positive association, whereas when R less than 0 indicates a negative association. Values of R near 0 indicate a very weak linear relationship. The strength of the linear relationship increases as R moves from 0 towards -1 or 1. The extreme values R is equal to -1 and R is equal to 1 occur only in the case of a perfect linear relationship. So we will understand these points by examples in later slide. So here in the example we can see that particularly if we take this example with correlation R is equal to 0, we can see that all the data points are scattered sparsely, and here we see there is no correlation or a linear relationship. This is somewhat looking like in the pattern of negative correlation, because when x is increasing, y is decreasing. So this pattern is visible here, but still data points are sparse and correlation value is -0.3, which is also suggesting the same thing. When correlation R is equal to 0.5, so here we can see that x is increasing and y is increasing too. So here the relationship is positive, and though points are scattered, so we can see R is equal to 0.5. So it's not a very good correlation, but somewhat better than 0. And here we can see correlation R is equal to -0.7. So points are getting close together, and here r is equal to 0.9, whereas here it is almost -1. So sometimes people think that if it's minus, it's something wrong, or we have to get positive. Positive is better, but in the correlation, it is not the case, because when we are getting negative correlation, it's just stating the fact that when x is increasing, y is decreasing. So explanatory variable is increasing and your response variable is decreasing. So even if it's showing the relationship, that's the relationship is the negative relationship. We should always understand what is no correlation, that is r is equal to 0. So we identify these more, that if there is no correlation, then there is no point to study further that study. So here we are, properties of correlation. Correlation makes no distinction between explanatory and response variables. What does this mean? This means that correlation between x and y is same as the correlation between y and x. R has no units and does not change when we change the units of measurements of x, y, or both. So we can take the example like if our x variable is height, it doesn't matter if it is in feet or centimeters, or if weight is in pounds or kilograms. This happens because we are standardizing all the observation in the calculating correlation. Third point is positive R indicates positive association between the variables and negative R indicates negative association. And the correlation R is always a number between -1 and 1. Here are the cautions. Correlation requires that both variables be quantitative. Obviously, we cannot compute a correlation between a categorical variable and a quantitative variable, or between two categorical variables. And correlation does not describe curved relationship between variables, no matter how strong the relationship is. The correlation R is not resistant. It means if there is any outlier, it would affect the correlation value. Correlation is not a complete summary of two variable data. Now we will learn about least squares regression. So regression line, if there is a linear relation between two variables x and y, we want to predict what y could be if x is known. So regression line is a straight line that describes that relationship, how a response variable y changes as an explanatory variable x. We can use a regression line to predict the value of y for a given value of x. So we are going to do an example. It's saying predict the number of new adult birds that join the colony based on the percent of adult birds that return to the colony from the previous year. Question is now, if 60% of adults return, how many new birds are predicted? So on x-axis, that is our explanatory variable, we know percent of adults returning, and on y-axis there are number of new birds. So for that we got this regression line, and this describes the overall pattern of the relationship. And if we want to know about the 60% of adults return, we will go from here to 60% on this line and we will predict it 14. Similarly, if you want to get for the 40%, you have to select from this point to here, and that would be almost approximately above 20. When a scatter plot displays a linear pattern, we can describe the overall pattern by drawing a straight line through the points. Fitting a line to data means drawing a line that comes as close as possible to the points. So as we are right now talking about line, and the formula of line is mx plus c. Similarly, we can see here the regression line formula is also similar to line formula, and it is saying y hat is the predicted value of the response variable for a given value of x. B naught is nothing but the intercept. What is intercept? The value of y when x is equal to 0. B1 is the slope, the amount of which y changes from each 1 unit increase in x. And x, you already know, is the value of the explanatory variable. So here is an example, and here is the regression line equation. So as we know, the intercept is where x is 0, the value of y is intercept, and here we can see that it is almost equal to 8. So here from software we got the value, it is 7.7757, and for the slope, the formula, as we know, the definition of slope is amount by which y changes for each 1 unit increase in x. So it can also be represented as rise over run. So for that, we can just take an example. If we are going to see this as just 1 unit change, so to get this value, we will get the rise, that is this value, over run, this value. So rise over run. And there is one other formula, that is m is equal to r, that is the correlation coefficient, multiplied by sy over sx. Sy is the standard deviation of y, and sx is the standard deviation of x. Both formula will give the same answer for the slope. Now least squares regression line. Because we are trying to predict y, we want the regression line to be as close as possible to the data points in the vertical y direction. So least square regression line of y on x is the line that minimizes the sum of squares of the vertical distances of the data points from the line. So if we have data on an explanatory variable x and the response variable y, the equation of LSRL is the same as we studied earlier. But what is least square regression? We will understand it in the later slide. So here are the facts for least square regression line. So different regression line will result if we change the values of x and y. So for here I took the earlier example and changes only 2 values of y, this one and this one. So here we can see that the least square regression line also changed. So even making change of any value of x and y can change the regression line too. As standard deviation are always positive, the sign of the slope and sign of the correlation will always be the same. Slope's other formula is equal to r, that is correlation, sx divided by sy. Sx is standard deviation of x and sy is the standard deviation of y. As standard deviations are always positive because we square it and then we take under root. We learned about this in last chapter. So it's always positive. So it's saying the sign of the slope and the sign of the correlation will always be the same. So if data points if you are able to see the correlation is in negative, then your slope will all be negative value. And the residual values that we get add up to 0. So if we add all the residual values, it will be 0. And as the sum is equal to 0, therefore the average will also be the 0. So predictions by regression line. For the returning birds example, the LSRL is, the formula we got is y hat is equal to 31.9343, that is the intercept, minus 0.3040, that is slope, x. Y hat is the predicted number of new birds for colonies with X% of adults returning. Suppose we know that an individual colony has 60% returning, what would we predict the number of new birds to be for just that colony? So for colonies with 60% returning, we predict the average number of new birds to be 13.69. Earlier we were using the scatter plot and seeing these values, and we were getting almost 14, getting this point. And now by this formula we are also getting the exact value, that is the 13.69. So here we got the Sarah's height was plotted against her age, and on x-axis we are having age in months, whereas height in centimeters. And the question is asking to predict her height at age 42 months and to predict her height at age 30 years. That is equal to 360 months. So here we can see for 42 months we can predict her height, but for 360 months it would be way more than the data we have been given. So we will see in the next slide. So for that, when we get regression line, we got formula y hat is equal to 71.95 plus 0.383x, and when we calculated for 42 months, y hat is equal to 88, and when we are predicting height at age 30 years, that is 360 months, y hat is 209.8. So our observed values are just from here to here, and we are predicting this value, which is far from the observed values. So this is known as extrapolation. So the use of regression line for prediction far outside the range of values of the explanatory variable is called as extrapolation, and these values are almost inaccurate because you have this much data and you want to predict for this point, so it's almost inaccurate. So here we are going to learn about the correlation and regression relationship. So least square regression looks at the distances of the data points from the line only in the y direction. As a result, the variables x and y play different roles in regression. Even though correlation R ignores the distinction between x and y, there is a close connection between correlation and regression. The square of the correlation, that is R square, is the fraction of the variation in the value of y. That is explained by the least square regression of y on x. And R square is sometimes called the coefficient of determination.